Welcome to the deep dive. Today we're diving into something, well, something massive, something everywhere. Gravity. Think about it. What keeps your feet on the ground? Why does the moon hang up there? Why don't planets just fly off into space? It's a question humans have wrestled with forever, and the story of figuring it out is, honestly, one of science's greatest hits. For this deep dive, we're digging into the theory of gravitation, straight from the classic Feynman lectures, our mission. To give you the inside track on this journey, from watching stars to Newton's big idea, Einstein's tweaks, and even the stuff we still don't get, you're going to get a real handle on what Feynman called this far-reaching generalization of the human mind. Plus, some pretty cool facts. We'll start with Newton's elegant little formula. F defragment looks simple, right? Look, we'll hit rewind, see how we even got there. It's more than math. It's about discovering nature follows this incredibly complete and simple rule.
It really is astonishing, isn't it? That one idea covers apples falling and galaxies swirling. And our journey to understand it really kicked off with people just looking up, watching the planets wander across the night sky.
Exactly. Ancient folks were obsessed. They eventually figured out planets go around the sun. Copernicus gets a lot of credit there.
Yeah.
But the exact paths, the speeds, that was the real head scratcher.
Right. And that's where Tycho Brahe comes in, late 1500s. He had this pretty radical idea for the time. He basically said, look, forget philosophical debates. If we want to know how planets move, we need data. Really, really accurate data.
So he spent decades just measuring, charting planet positions like crazy from his observatory, ended up with these huge detailed tables.
Yeah, mountains of data, the best anyone had ever seen.
And after Brahe died, this data landed in the lap of Johannes Kepler, a mathematical whiz. He didn't just file it away. He dug in, lived in those numbers, and as Feynman puts it, he discovered from the data some very beautiful and remarkable but simple laws regarding planetary motion.
It was like finding hidden music in the numbers, yeah. And these laws, his three laws, totally changed the game.
Mm-hmm.
The first one, planets don't move in perfect circles like everyone assumed. They move in ellipses.
Ellipses, right. Not just any oval shape, but a specific mathematically defined curve, like a stretched circle, with the sun at one of the focus points.
Precisely. A subtle shift, but huge implications. It broke from that ancient idea of perfect celestial circles.
Okay, so that's the shape. What about how fast they move? That was Kepler's second one, wasn't it?
Yes, and it's about speed. Planets don't just cruise along steadily. They speed up when they get closer to the sun, and they slow down when they're farther away.
Okay.
Specifically, imagine a line connecting the sun to the planet, the radius vector. Kepler found it sweeps out equal areas in equal intervals of time.
I think I remember this. So like in 1 month, that line sweeps across a certain slice of space.
Exactly.
And the area of that slice is always the same, whether the planet is close and moving fast, making a short, fat slice, or far away and moving slow, making a long, thin slice.
You got it. It's a really elegant conservation principle hidden in the motion.
Cool. And the third law, you mentioned it connects different planets.
Yeah, this one's maybe the most profound because it relates one planet to another. It's not just about a single planet's orbit anymore. It says the time it takes a planet to orbit, its period, is related to the size of its orbit, specifically the major axis, in a very precise mathematical way. It's proportional to the 32 power.
Whoa, okay, the 32 power sounds specific, but the main point is...
The main point is there's this strict mathematical lockstep between how big a planet's orbit is and how long it takes to go around. It applies to all the planets. It showed the whole solar system was playing by the same rules. A deep consistency.
Okay, so while Kepler's sorting out the heavens back on Earth, Galileo is figuring out basic motion. Inertia. That was key.
Oh, absolutely essential. Galileo's principle of inertia, the idea that an object just keeps going in a straight line at constant speed unless a force acts on it, was revolutionary. Before him, people thought things naturally slowed down, needed a constant push. But Newton took Galileo's idea and added a crucial layer. He realized force doesn't just change speed, it changes direction too.
So if a planet isn't flying straight, but curving,
then there must be a force acting on it, constantly pulling it off that straight path.
And Newton figured out where that force pointed, not like sideways pushing it along. Feynman mentions those invisible angels pushing planets.
Exactly. Not angels pushing sideways. Newton showed the force had to be pulling the planet directly towards the sun, centripetally. He used Kepler's second law. The equal area is 1 to prove mathematically the force had to be central, pointed right at the sun.
Wow. Okay, and then he used the third law.
Yes. Using Kepler's third law, the one linking period and orbit size, he deduced the strength of that force. He found it weakens with distance. Specifically, it follows an inverse square law, Double the distance, the force drops to 1/4. Triple it, it's 1/9. That precise relationship.
And here's the giant leap, right? Newton didn't just say, okay, this explains the planets. He went bigger, much bigger.
Oh, massively bigger. This was his genius. He proposed this wasn't just a solar system force, it was universal. His grand hypothesis, everything pulls everything else. The apple falling from the tree, the moon orbiting Earth, the planets orbiting the sun, it's all the same force.
Unifying the heavens and earth, incredible. But wait, the moon doesn't look like it's falling. It stays up there.
Right, doesn't get closer. But think about inertia again. Without gravity, the moon would fly off in a straight line. It is falling. It's constantly falling away from the straight line that it would pursue if there were no forces. It falls around the Earth.
Okay, that falling around idea needs unpacking. The bullet analogy helps here, doesn't it?
It's a great analogy. Drop a ball, it falls, say, 16 feet in the first second.
Right.
Now, fire a bullet horizontally, it travels a long way horizontally, but vertically. It still falls 16 feet in that first second.
Okay.
Now, imagine firing that bullet really fast. So fast that as it falls 16 feet downwards, the Earth's curved surface also drops away 16 feet beneath it.
Oh, so it falls, but the ground curves away just as fast. It never gets closer.
Exactly. It keeps falling, but it never hits the ground because the Earth curves away. It's in orbit. That's what satellites do. That's what the moon does.
Like Gagarin, orbiting at 5 miles per second, just constantly falling around the Earth. Mind-bending.
And fun fact, Newton actually calculated the moon's fall rate early on, but his numbers didn't quite match because the accepted value for the Earth's size was off.
No way. What did he do?
He didn't publish. He waited. About 6 years later, a more accurate measurement of the Earth came out. He redid the calculation, and boom, beautiful agreement. Patience and rigor.
Amazing. And this universal law, it didn't just confirm Kepler's laws, it explained them, right? Like the ellipses.
Precisely. Newton's inverse square law mathematically predicts that orbates must be ellipses. Kepler's first law just pops out of the physics. No extra assumptions needed.
And it explained other stuff too, like tides. Those are always mysterious.
Totally mysterious. People had weird ideas. But Newton's law nailed it. It explained why we get 2 high tides a day, not just one on the moon-facing side.
How does that work again? Differential pull.
Exactly. The moon pulls on everything, but slightly harder on the closer side of Earth than the center, and slightly harder on the center than the far side. So the water on the near side bulges towards the moon because it's pulled hardest.
Okay.
But on the far side, the solid Earth is pulled away from the water there more strongly than the water itself is pulled. So the water effectively gets left behind, bulging out away from the moon.
2 bulges. Makes sense. Differential stretching, kind of.
Yeah, you got it. And that same principle, everything attracts everything else, explains why big things in space like planets and stars are basically round.
Just gravity pulling everything inwards equally from all directions.
Yep. Pulls it all together into the most compact shape, a sphere. Rotation squashes them a bit, makes them slightly elliptical or oblate, but the basic roundness comes from gravity.
Okay, so gravity isn't just local. It reaches out. Let's talk cosmic scale. There was that cool discovery with Jupiter's moons in 1676. Rumor.
Old rumor. A fantastic story. He was timing Jupiter's moons very carefully, watching them disappear behind Jupiter and reappear. And he noticed something odd. Sometimes they reappeared a bit early, sometimes a bit late, compared to his predictions.
Like Jupiter's gravity was messing with them.
Not exactly. He realized the timing difference depended on whether Earth was closer to Jupiter in its orbit or farther away.
The travel time of light?
Bingo. When Earth was farther, the light from the moons took longer to reach us, making them appear late. When Earth was closer, the light arrived sooner, making them appear early.
So by timing Jupiter's moons, he actually figured out light doesn't travel instantaneously. He got the first estimate for the speed of light.
He did. An amazing piece of deduction, all thanks to meticulous observations driven by understanding gravitational orbits.
Wow. Okay, fast forward. Uranus. Discovered, tracked, but okay. Its orbit was a bit wobbly, right? Didn't quite fit Newton's predictions, even accounting for Jupiter and Saturn.
It was a real problem, a weird orbit, as Feynman says. It looked like maybe Newton's laws weren't perfectly universal after all.
Yeah.
This was potentially the death of this wonderful theory.
High stakes.
Very. But 2 mathematicians, Adams and Leverrier, had another idea. What if there was another planet out there, unseen, whose gravity was messing with Uranus?
A ghost planet.
Essentially. They independently used Newton's law, did the incredibly complex math, and predicted where this unseen planet should be. And astronomers pointed their telescopes to that spot in the sky, and there it was, Neptune.
Boom! Found by math and gravity alone. That must have been a massive confirmation for Newton.
Monumental. It showed the incredible predictive power of the theory. And we see gravity working way beyond Neptune, too.
Like with stars.
Yeah, double stars. Pairs of stars orbiting each other in perfect ellipses, just like Newton predicted. We see it in globular clusters, these big, dense balls of thousands of stars, all held together by their mutual gravity.
The scale is just hard to grasp. How far does this reach?
Enormous distances. Globular clusters might be 100,000 times bigger than our solar system. Entire galaxies, hundreds of billions of stars, held together by gravity, spanning maybe 50,000 to 100,000 light years across.
Mind-boggling.
And it doesn't stop there. Clusters of galaxies, huge collections of galaxies, themselves gravitationally bound, stretching across tens of millions of light years. The inverse square law just keeps on working, as far as we can tell.
Can you even imagine that scale? It even leads to ideas about how stars are born, right? Gravity pulling gas clouds together.
That's the prevailing theory. Giant clouds of dust and gas in space start to collapse under their own gravity, fragmenting into clumps that heat up and eventually ignite as stars.
Is there visual proof? Feynman mentions some photos.
There is suggestive evidence, like observing dense regions within nebulae. Feynman mentions one specific, though maybe debatable, instance where astronomers thought they saw two new bright spots appear over just 7 years in a nebula photo comparison. Direct proof is tricky, but it fits the gravitational picture.
Okay, so gravity shapes the cosmos. But what about measuring it here? Between everyday objects, it's weak, right?
Incredibly weak on that scale. That's the challenge Henry Cavendish tackled in the late 1700s.
The famous experiment to weigh the Earth. How did he measure such a tiny force?
He used a torsion balance. Basically, two small lead balls on the ends of a rod, suspended by a very fine wire. Then he brought two much larger lead balls near them. The tiny gravitational pull between the small and large balls caused the rod to twist the wire ever so slightly. By measuring that tiny twist, he could calculate the force.
Delicate work.
Extremely. But by measuring that force, he figured out the value of g, the gravitational constant in Newton's equation. And once you know g, and you know how strongly Earth pulls on things, you can calculate the mass of the Earth.
So he weighed the Earth without putting it on a scale. Amazing.
It was a triumph. And its success gave scientists huge hope. Maybe all of nature's phenomena had these beautifully simple underlying laws.
But it still leaves that big question hanging, doesn't it? We know how it works, thanks to Newton's fact-G-frac, but what is it? What's the machinery?
Exactly. Newton himself was very clear on this. He described the effects, the mathematics, but he made no hypotheses about the underlying cause, the machinery.
And nobody since has really figured out the why.
Nope. No one has since given any machinery. Physical laws often have this abstract quality. They tell us how things relate, often with incredible precision, but the deeper what or why can remain elusive.
Have people tried to invent mechanisms?
Oh, sure. Feynman mentions one idea from the 1700s involving tiny invisible particles flying everywhere and objects blocking them, causing a push towards each other.
Sounds complicated. Did it work?
It failed. Because if that were true, a planet moving through this sea of particles would feel resistance. It would slow down in its orbit. And planets don't do that. That's the problem. No machinery has ever been invented that explains gravity without also predicting some other phenomenon that does not exist.
Huh. So it's just a fundamental force. How does it compare to other forces, like electricity?
Well, there's that striking analogy. Both gravity and the basic electrostatic force follow an inverse square law. That's neat. But the difference in strength is just astronomical. Take two electrons. Their electrical repulsion is vastly, vastly stronger than their gravitational attraction.
How much stronger?
The ratio is 1 divided by 4.17 times 10 to the power of 42. That's a 1 with 42 zeros after it.
Whoa. Okay, that's 4.17 million billion times stronger. Roughly.
Something like that. It's an utterly enormous number. Gravity is incredibly weak at the particle level.
Where does a number like that come from? Is it just random or does it mean something?
That is one of the deepest mysteries in physics. People have wondered if it's connected to the age of the universe. If you, say, compare the age of the universe to the time it takes light to cross a proton, you get another huge number, roughly in the same ballpark, 1042.
Seriously?
Yeah.
That's weirdly coincidental.
It is. It led to speculation. Maybe the strength of gravity, G, isn't constant. Maybe it's been changing, getting weaker as the universe expands.
Would we test that?
People have tried. One argument looks at the sun's brightness and Earth's history. If G was, say, 10% stronger a billion years ago, the sun would have been much hotter, and Earth would likely have been boiling maybe 100 degrees Celsius hotter. No liquid water, no life in the seas as we know it.
So the fact that life did evolve suggests G hasn't changed much.
That's the argument. Feynman calls it not very convincing, but it's one piece of evidence suggesting G is likely constant. But the origin of that huge 10-42 ratio, still a profound puzzle.
Okay, another weird thing about gravity. It seems perfectly linked to inertia, right? The m in Funapal is the same m in 40D.
Exactly. Gravitational force is precisely proportional to inertial mass. That's why, in a vacuum, a feather and a lead ball fall at the exact same rate.
And it explains weightlessness in space, too.
Yep. The astronaut and the spaceship are both falling together around the Earth. Since they're accelerating identically due to gravity, there's no relative force between them. They feel weightless. Experiments by Ovis and later Dick confirm this equivalence between gravitational mass and inertial mass to incredible precision, like 1 part in a billion. It's a very deep feature.
But even Newton's amazing law had limits, which brings us to Einstein. What was the problem?
The big problem was speed. Newton's law implies gravity acts instantly. If the sun vanished, Newton's law says Earth would instantly fly off its orbit.
But Einstein showed nothing travels faster than light, right? Not even gravity.
Exactly. Einstein's theory of relativity sets a universal speed limit, the speed of light. Instantaneous action at a distance conflicts with that fundamental principle. Newton's law needed an update for high speeds and strong gravity.
So Einstein fixed it. How did his theory change things?
Einstein's general relativity pictures gravity not as a force between masses, but as a curvature of space-time caused by mass and energy. And a key consequence is that anything which has energy has mass in the sense that it is attracted gravitationally.
Anything with energy. So, even light. Light has energy. Is light affected by gravity?
Yes. That was one of the most dramatic predictions of general relativity. Because light has energy, its path should be bent when it passes near a massive object.
Like the sun.
Like the sun. Einstein predicted that starlight passing close to the sun would be deflected by a specific tiny amount.
And they actually measured this. How you can't see stars near the sun normally?
During a total solar eclipse, when the moon blocks the sun's light, you can briefly see the stars nearby. Astronomers did exactly this in 1919. They photographed the star positions during the eclipse and compared them to photos of the same stars taken when the sun wasn't there. The stars had shifted, their light bent by the sun's gravity, by almost exactly the amount Einstein predicted.
Wow. That must have been huge news, seeing gravity bend light.
It was a stunning confirmation. It cemented Einstein's theory as our best description of gravity.
So, Einstein improved on Newton. Is that the final word on gravity? Or is the story still going?
Oh, it's definitely not finished. While general relativity works beautifully on large scales, it doesn't mesh with our other great theory of the universe, quantum mechanics, which governs the very small. Gravitational effects are so weak at the quantum level that, as Feynman puts it, the need for a quantum theory of gravitation has not yet developed in terms of experimental necessity. We haven't found situations where we absolutely need both theories at once.
But conceptually, they don't fit together.
Right. They describe the universe in fundamentally different languages. Reconciling Einstein's smooth geometry of space-time with the fuzzy, probabilistic world of quantum mechanics, finding a theory of quantum gravity, is perhaps the biggest challenge in fundamental physics today. This last modification has not yet been completed.
What an incredible story we've traced. From Kepler watching planets to Newton's universal insight that explained apples and moons, then seeing that law predict Neptune out of thin air, reach across galaxies, even down to Cavendish, measuring it in a lab. And yet, after all that, these deep questions remain.
They absolutely do. We have these incredibly precise mathematical descriptions of how gravity behaves. We can predict its effects with amazing accuracy. But the fundamental nature of it, the machinery Newton didn't guess at, the why behind the curvature of spacetime, or how it fits with quantum reality, that core essence is still a profound mystery.
Which leaves us with something to think about. Consider gravity's power over cosmic scales, holding galaxies together, versus its almost unbelievable weakness compared to other forces between tiny particles. And that staggering number, 10 to the 42, that captures the difference. What does that immense ratio tell us about the deep rules of our universe? Is it just a random fact of our reality, maybe fine-tuned so we could be here? Or is it a flashing clue, pointing towards an even deeper, unifying theory we haven't found yet? Something to ponder until our next deep dive.